Okay, so welcome back to another lecture. And last few lectures, we have been talking about structures and particularly frames. So trusses we have already completed, and frames and membrane, so not membrane, machines. Frames and machines, we'll just try to do some finishing touches in this lecture. And then the main topic of this lecture is cables. We'll be talking about that. Okay, so this is an example that we have seen in the last class, and this was quite straightforward. So where at the point A, we were able to get the two reactions as well as the tension in the rope GD. We were able to solve for that right from the beginning, right? But and then we, after finding the reactions, then we moved to individual bodies, and then we were able to solve for the internal forces, Cx, Cy, Fbe, and so on. Now let us consider this example where, as I wrote in the heading, so this structure, it looks indeterminate to start with, right? So we have members AC and CB, which are pinned together. And now if you look at the onset, it appears that we have two reactions here, AX, AY, and similarly BX, BY are two reactions here. So we have total 4 unknowns, and right from the beginning, we will not be able to solve for the 4 unknowns because we have 3 equations in 2D. So, but the problem can be solved if I consider the two bodies distinctly. So if I separate these two bodies distinctly, then on, let's say, body AC, I have two forces AX, AY are the reactions. Then CX, CY are the internal forces which appear equal and opposite on two bodies. So that's Newton's third law. So if Cx is in the right direction on body AC, then it is on the left direction on body BC. Similarly for Cy. And then external load P and Q are already there. So now if we count the number of variables or number of unknowns that we have, so we have 2 for A's, 2 for C's, and 2 for B's. So total we have 6 unknowns, and we have two bodies. So I can write 3 equations for this body, I can write 3 equations for this body, and this problem can be solved. So yeah, so we have 6 variables and 6 equations, and now problem is determinate. So we can solve this problem, and by solving 6 equations, 6 variables, so that is one way. So that's what I've written here. So you can solve it in one way, or the another option of one. So this is the first way is more tedious. You have a system of 6 equations, 6 variables. Again, you have to write some code to solve 6 equations, 6 variables. The other approach is if I go here and consider the body or consider the system A, C, B, and if I balance moment about point B, right? So if I consider the balance the moment about point B, then I can solve for AY directly, right? So if I, let me draw it. Okay, now if I consider this system, and now the external forces are, so these are the external forces, and P and Q. Now, when I consider this together, the C forces at node C are internal, and they are not accounted for. I mean, we don't have to worry about that. So now if I balance moment about this point B, then the only, I mean, P, Q, and this AY. So these 3 forces, AY, P, and Q will come into picture, and geometry is known. So therefore, AY can be calculated. Similarly, if I balance moment about point A, then BY can be calculated. And therefore, out of 6 variables, now by using this approach, we have calculated, 2 variables we have calculated, and we have 4 unknowns. And again, so that's the simple approach, little bit simpler. we can solve for AY and BY and we can proceed. Okay. So, so that's the, finishing touches to frame. And the last topic is machines. So machines is again it's very similar to frames. The only difference is that here things can move, right? So machines are structures to transmit and modify forces. And just give me a minute. Okay. And so suppose we have input force, like it's a plier to cut some wire or something like that. So here we are applying a force P, which is the input, and then there is an output which is which acts on the wire, which is Q. And the question is to find a Q for a given value of P. And machines are non-rigid, they can move. So what we will do is we will use one of the components as a free body, right? So you can see that there are two bodies as part of the plier, and we will consider one of them as a free body and to do the analysis. So now if I, this is the forces, and if I apply Newton's third law, then this force acting on the wire will act equal and opposite on the machine or on the plier. And now if I separate this one part out, right? So this is the one part out. Then we have to include these reactions which comes from each other part, right? AX, AY, which are going to be equal and opposite. And yeah, so now I can analyze the system. So I can say if I balance moment about point A, so if I balance moment about point A, then we have, P times A will be equal to Q times B. So yeah, so from there we can get what is the force Q, which is like, like a lever effect. So A by B times P. Okay, so I think that's all for the machines part. And now we will start the topic for today, which is the cables. Okay, so can you see the screen, cables?
Yes, sir. Yes, sir.
Hello?
Yes, sir. We can see the screen.
Okay, thank you. So now cables are a special topic. As such, they are not rigid structures, but they are a special topic for structure design and structure analysis. So it is, it's really good to talk about it. And so cables have a lot of wide applications, as you can see in the starting slide. So the top two are, cable cars or tramway, or these cable cars, which are quite common. At least some places you definitely find it. So now here, this is the first kind of problem that we are going to encounter, where there is a point load acting on the cables, right? Of course, this is a more dynamic problem where these cables are also moving. In this class, of course, or in this course, we are going to talk about right now where these are stationary, right? So let us say they are hanging down. What is the shape of the cable? What are the, what is the tension? Where is the maximum tension? What is the shape of cable? These are some of the questions we'll try to answer in this lecture. The second type of problem is what you can see on the left side, bottom left side of the figure, which are called as suspension bridge, right? So these are bridge, which this picture is, I think, from US, some very famous bridge. But like this, you'll find these bridges in many places, right? So basically here, the interesting thing is that this is the cable, right? So this is the cable that you can see, and there is a uniformly distributed load by the road, right? So if there is a road which hangs kind of, so these cables support these very heavy loads, and we will try to analyze this cable, again, the tension, the shape, and so on. And the third type of problem that we will see is, cables which are hanging on their own weight, right? So there is no external load except their own weight. So this is the third category of problem, which is called as a catenary cable, and we will analyze that as well. Okay. Now let me ask our quiz masters, Ayushman and Satyam. So can you identify what is this picture, or anyone else would like to give a try? I don't know if they are present. Ayushman. Yes, someone said. Ritu, yeah, go ahead. Someone internet is not working. Anyway, Ayushman Jha, are you present?
Yes, sir. Like initially, because of the structure, I thought it was a London Bridge, but then there I see mountains, so
London
that's
Bridge.
not the case. That's
Wow.
definitely not the case because I see the mountains, but because of the structure that does resemble the London Bridge on Thames.
Okay, that's great. It's a good guess. Okay, what's his name? Satyam. Is Satyam present?
Yes, sir, I am present.
Yeah, any guess from your side, Mr. Satyam?
I'm not sure. The upper structures, the four structures
Victoria
that
Bridge,
have.
Mandi.
Mhm.
That's the Victoria
Okay,
Bridge in Mandi.
many of you guessed it correctly, and you have also, I think, written in the chat as well. So this is the bridge. Okay, but let me ask you a question. What is the relation of this picture with all of us? That's a better question. Okay, so
We can see a
great.
cable
So
running through the length of the bridge.
Pratiksha got it correct. So this is the bridge which is responsible for the IIT Mandi logo. So I'm sure all of you know this IIT Mandi logo. So this is the representation of this structure here, and many of you said it correctly. So it's a Victoria Bridge in Mandi, and this is again a suspension bridge. So the reason I'm talking about is the suspension bridge. As you can see here, so these are the cables which which support the structure of this bridge. It's not a very big bridge, but yeah, it's a famous structure in Mandi. Okay, so coming to our our topic. So the first type of problem is the problem with concentrated loads, right? So let us say if I have got a cable which is AB, and we have got three loads, P1, P2, P3. Now, so the given is we have these three loads, P1, P2, P3, and we want to find, and of course we are also given the position of the loads X1, X2, and X3, and we want to find the shape of the cable, as well as we want to find what are the tensions at different points. So so for doing the analysis, first of all, we are going to make the basic assumptions. So the basic first assumption is that, of course, the loads are vertical and they are given concentrated loads. The second assumption for now is the weight of cable is negligible, right? So for example, if you have got cable cars hanging, or if you have road, you have load. So then with respect to the weight of the cable, we will neglect it. Although in the third problem, we are not going to consider this assumption. The third assumption is that the cable is flexible, and which means that resistance to bending is small, right? So it can easily flex, it can easily bend. And the portion of cable between successive loads may be treated as two-force member. So now, since there is no weight, excuse me, or we are neglecting the weight of the cable, so then let's say between C1 and C2, we will consider it as a two-force member, right, between C1 and C2. So, so now if we consider the first analysis, okay, so first analysis is we consider this whole cable as a free body. So if I consider this whole cable as a free body, it is hanging from point A and hanging from point B. So there are two reactions, unknown reactions, AX, AY, BX, BY. And these are external loads, P1, P2, P3 given to us. And so if I consider the cable as a free body, the slopes at A and B are not known. And therefore we have to use your AX and AY as four unknowns. We have, which is the four reactions and three equations, right? So we can write for this whole structure, we can write three equations. Some moment is equal to, about a point is equal to 0, and fx is equal to 0, fy is equal to 0, and we can we can write these three equations. And let me write it here. So I can write, let's say, moment about point B is equal to 0, and then I can write summation of fx is equal to 0 and summation of fy is equal to 0. Okay, so if I write the first equation, moment is equal to moment about point B is equal to 0, then Bx, By vanishes. What I have is Ax multiplied by small d plus Ay multiplied by L. So these are clockwise moment, should be equal to P3 times L minus X3, which is the anti-clockwise moment, plus P2 times L minus X2 plus P1 times L minus X1, right? So this is one equation I can write, and it's an equation in Ax and Ay I can write, right? So I'm not writing the first equation, you can write it, it's quite straightforward. Similarly, we can write moment, net force in y direction is equal to 0, means Ay plus By should be equal to P1 plus P2 plus P3, and I can write Ax plus Bx should be equal to 0. So these are the three equations that we can write, but we have four equations, so we cannot solve it directly. We need one more information, right? So this equation we have already written, moment about point P is equal to 0, and this is basically a relation between Ax and Ay, right? So this we can write. Now we need an additional equation, and that additional equation will be suppose if we know some point is known. For example, say, let us say if point C2 is known, and when I say point C2 means x2 comma y2 are known. So if, let us say, I know, of course x2 was already given, suppose I know y2, the position of y2 of point C2, then we can write the moment equation about point C2 for a given part, for a given, it's not written here, for part of the cable, which is AC2, we are writing this equation. So now I cut a section here at C2, and then I analyze a part AC1, C2, right? So this is here drawn here, AC1, C2. If I write this equation, summation of moment about this point is equal to 0. So what I'll get is P1 times x2 minus x1. So this is the anti-clockwise moment, and then I'll have the clockwise moment will be equal to Ax times y2 plus, that is also anti-clockwise, so that is Ay times x2, right? So this is the another equation that we can write if y2 is known, right? So now I have two equations and two variables, right? So the one equation is from this this moment balance. We have equation number 1, and this is equation number 2. So equation number 1, equation number 2, I have two unknowns, Ax and Ay, and I can solve for so Ax and Ay can be solved. And once Ax and Ay can be solved, then you can similarly solve for other reactions. Bx, By can be calculated, And similarly, we can solve for displacement of point y1, right? So we can solve for, we can take the section AC1 and we can then solve for what is the displacement of point y1. If once ax and ay are known, then I can draw the free body diagram for AC1 and calculate the y1 can be known. Similarly, I can draw the free body diagram for AC1, C2, C3, means from A to C3. And again, AX, AY are known. So again, balancing moment about point C3, we can calculate the Y3. And similarly, then balancing the forces, we can calculate the, the tension, the forces. Right? Now, the next question comes, which is written here, is what will be the maximum tension and what or slope. So now the question comes, where is the maximum tension? So now here at point C2, if I write the force balance, so not just at point C2, but for this part AC2, if I write the force balance, so if I do summation of Fx is equal to 0, what it says that Ax plus T cos theta, where theta is this angle, this should be equal to 0. This is the first equation. And similarly, if I do Fy, summation of Fy equal to 0, so then I have P1 plus P2 plus T sine theta should be equal to Ay. Okay. So these are the two equations that we can write from force balance. Now the first equation says that Ax with a negative sign will be equal to T cos theta, right? So what this says that the horizontal component of tension is always going to be constant throughout the cable, right? So you see from this part, Ax and Ay have been calculated. So this is a number which is constant. Ax is known. So if Ax is known, means T cos theta, irrespective of the position where we are taking, the horizontal component of tension is always going to be constant in the cable, throughout the cable. So Tx, or the horizontal component of tension, will be same. The vertical component will change, and that will be maximum where so the maximum tension will take place where your slope is maximum, because your horizontal component is same. And let us say at point A, where your vertical component is maximum, that is where your net tension is going to be maximum, right? And more about that we will see in this part. The next part is cables with distributed load. So now suppose I have got a cable which where instead of having point loads, we are having a distributed load, like as you can see here in this picture. So for such cases, the shape of the cable will have a very nice smooth curve. So in the previous case, it was like a continuous function, but its derivative was discontinuous. But in this case, we are going to have a very nice curve, and for a distributed load. And again, if I consider a small part of it, the tension force will always be along the cable. So the internal tension force will always be along the small. So if I consider this part, so the tension will act only along the direction of the cable, which means along the tangent to the curve. Okay. Now to do an analysis for this, if we consider the free body of the portion of cable extending from the lowest point C to a given point D. Right? So now I have some given point D, but now the diagram that we are drawing is from the lowest point C to a point D. This is a very important point, and that's why it is highlighted and underlined, that for these kinds of problems, the diagrams have to be drawn from with a cut section taken at the lowest point to any other point of interest. Okay. So now once I draw this diagram, if I draw the force at point C, we know that since it's the lowest point, its tangent is horizontal. So therefore, the tension is going to act horizontally. So the direction of this tension here, I know it is like this. Also, as we have seen in the previous case, the horizontal component of tension is going to remain constant. So therefore, this horizontal tension, so at point C, there is no vertical tension. So therefore, this thing we are representing as a value called as T naught, because that's going to be constant. And then the other point, arbitrary point that I've considered, point D, there is a tension T, which is acting along the tangent at point D. Then in between point C and point D, there is a lot of distributed load, and let us say that has an equivalent load which is acting at, let's say, which has the equivalent force as W, acting vertically downwards. So now this system is in equilibrium, and therefore, directly also you can say that T cos theta should be equal to T naught and T sin theta should be equal to W. Or you can draw a triangle, and now I can arrange these three forces, T naught, T and W, so that these three resultant of these three forces is 0. And this T acts at an angle theta, so this is known. So again, from here I can write same thing, T cos theta is T naught, T sin theta is W. And the magnitude of tension at point D, which is capital T, is equal to square root of T naught square plus W square, and the angle, the slope, is equal to W by T naught. So this is the generalized expression for tension and slope for a cable with distributed load. Okay, so this is the same thing that we have seen. So I have considered a section from C to D, and we have written this expression. And so again, some of the lessons is, one thing is the horizontal component of T is uniform over the cable, because T cos theta is equal to T naught, which is same at all points on the cable. Number two, the vertical component of T is equal to magnitude of W measured from the lowest point. So the vertical component of T, which is T sin theta, so T sin theta is the net load acting on the cable from the lowest point, right? So from the lowest point, so let's say if I'm talking about the right side, it is from point C to point D, whatever is the net force acting downward, that is the vertical component of tension at point D. Okay. And so the third important point is the tension in the cable is minimum at point C, or at the lowest point, and it is going to be maximum at the end point. So either A or B, it is going to be maximum. And for this diagram, we can say that the tension is going to be maximum at point B, because we have got a lot of, provided this load is more. Okay. Now, a special case of this load is when these red arrows are all uniform, right? They are of uniform size. And that is what leads to the suspension bridge problem, where you have, let's say you have a cable AB, but I have a road going below or some kind of load, which is uniform distributed. So now we have W, which is weight per unit length, which is constant. And now we have got, so now we'll consider the cable from the lowest point C. So this is point C. And so now again, we'll consider, C to D for the analysis. Now, internal tension and slope we have calculated in the previous case. So the tension is equal to T naught square plus W square, where W is the net load. Now here, this W is going to be W. So this capital W will be replaced by W times X. So if I'm considering any point, so this is the point C, and sorry, it should be horizontal. So if I consider, so this is X. So the net load acting here is Wx, small w into x, so it becomes W square x square. And now if I draw the, so this is the tension value at point D that we have calculated, and the slope is also known, which is Wx by T naught. Now the next question comes is how do we get the equation of this curve for this suspension bridge? And to do that, we have to balance moment at point D. So to get the shape of the cable, we'll balance the moment about point D for this cut section. And if I write moment of D is equal to 0, then it is T naught times Y. So T naught times Y is the moment due to T naught in the clockwise direction. And the anti-clockwise moment is, the load is Wx, and it is, since it's uniformly distributed, it is acting at x by 2. So therefore Wx into x by 2 minus T naught Y is equal to 0. And this equation leads to equation of Y. So therefore in suspension bridges, the pictures that we have seen before, the curve that forms this suspension bridge, that is an equation of a parabola, right? So the cable forms a parabolic curve. Okay. Let me try to complete this. The last topic is catenary cable. So catenary cable is like a transmission tower line cables. So these cables hang with their self weight. So now there is no external weight except the weight of the cables itself. So now let us say I have got a cable which is hanging something in its with its own weight. This is the lowest point C. Now let us say if I consider a unit distance here, and if I consider the same unit here. So this is a unit length, and this is again a unit length, let's say 1 meter. So I hope all of you will agree that here the weight is less, and here the weight is more. Because here in 1 meter, you'll have less amount of wire coming here. But in this 1 meter, you'll have more, transmission cable present here, and here the weight is going to be more. So therefore, there is, load, but it is not uniformly distributed. This load is proportional to the length of the cable, which is different at different points, because here the slope is more, here the slope is 0. So therefore, this load is measured. So this is measured by distance S, which is the arc length. So this S here, what you are seeing, S is your arc length. Okay, which is different at different points. So now here, if loading of the cable, again, the same story, we consider the lowest point to an arbitrary point D. And if I consider the forces, so again, you have T naught, you have T, but now here the load is acting, which is W times S, where S is this arc length, you can see here, right, or path length. So this is your S. And again, if we consider the force triangle, we have the same force triangle. So many things are same. But now if I consider a differential element, now because I want things in terms of X and Y, if I write dx, so dx is from this figure, you can see is ds cos theta. And the cos theta is T naught by T. We know that, right? Because T is equal to T naught cos theta. So, T cos theta is equal to T naught. So this is what we have substituted here. And cos theta, now, now here this is another we have introduced another variable, which is C. Now this C is just to simplify the mathematical analysis, and we will see it really simplifies things. So if I introduce C as T naught by W, and if I see this expression here, then if I substitute T naught as WC, then the W thing will come out of the square root and we will have this expression. And now this thing I can substitute here. So this T naught is WC, right? So this is WC, and T is equal to this expression, what we have written here is something like this. Again, W cancels. C, I can take it below the square root and I get an expression something like this. Now this expression can be integrated, right? So now I have dx is equal to ds by this expression. And I hope you will be able to recall that this integral is basically your sin h or sine hyperbolic inverse derivative, integral. So when I integrate this thing, it is from 0 to s, c times sine hyperbolic inverse s by c, which we can apply the limits, and we get this expression c s, which is the path length or the length along the cable, is equal to c times sine hyperbolic x by c. And maybe I think I'm will cover this in the next class. So so I think that's all for today. We will continue with the final touches in the next class.